This will be a summary of the week 3 lecture content. This week we continue some of the previous topics and introduce some new ones. So like the previous week, we start off with an interactive lecture based on the readings. So let's see some of the key points in the questions this week. For question 1, when we speak of variation, we divide it into two broad categories. First is random variation or common cause variation. This refers to the background variation of a system or process. For example, if you drive to work every day, the exact amount of time this takes will vary. However, it will vary within a predictable range. So the counterintuitive point here is that the random common cause variation is actually the predictable type. On the other hand, we have non-random or special cause variation. This refers to data which indicates that something unpredictable has occurred in a system. For example, if you're driving to work one day and discovered that your whole street is backed up because of an accident at the end of the street, the amount of time it will take you to get to work will be greatly different than on every other day. So what we are trying to do is to see the difference between predictable and unpredictable sources of variation. For question 2, we can continue with the car example. Distinguishing between the two types of variation is essential here. If we were to interpret the longer trip one day as being indicative of a broader change, we might decide that we need to get up half an hour earlier each day. However, this would be a misinterpretation of the special cause of variation. As a counter-argument, we might point out that a value which is considered to be a statistical outlier may not necessarily indicate a special cause. It is possible, to some degree, to have a very quick or very slow trip to work on a given day. This may suggest a special cause in the statistical sense, but may simply be an extreme value owing to random variation. This leads to question 3. Should we treat outliers in data as noise or signals? This question is important because there are those who will scrub data for outliers before doing analysis, which is often a mistake. But why is it a mistake? An extreme value in our data, an outlier, suggests a special cause of variation. We can't be sure of this, but we need to investigate. In other words, we should treat outliers as signals until we are reasonably sure that they are noise. For example, let's take a manufacturing line with a sensor. Unless we change the process, the data collected by the sensor should remain within a predictable range. One day we discover that the value is far outside of the range. We don't know why, but it would be a mistake to disregard the data as noise. So we investigate. Upon investigation, we discover that the sensor is damaged, perhaps. Then, and only then, can we make the pronouncement that the data was bad. Replace the sensor and delete the bad data. So what might be a counter-argument? Perhaps we are interested in the data around the median, and extreme values aren't of interest. For example, let's say we have a product for mainstream car owners. We may want to filter our data because the preferences of luxury car owners aren't really of interest in our analysis. Question 4. The chapter introduces change concepts. Something which we'll be looking at in more detail next week, so we only have a few to choose from here. Okay, let's take this one. Evaluate the purpose and challenge why you are doing something. And let's think about the trains. What do the trains spend a lot of time doing? A lot of starting and stopping at different stations. One purpose for this is to fill up the train. What if we broke them up and deployed them as shorter trains? 4 carriages rather than 8. That way, trains would fill up after a smaller number of stops and could proceed to the city. Essentially something that's already being done but at a more granular level. Now, would that be practical? Probably not. And not just because we would need more drivers for the trains. One of the rush hour constraints in the city stations is how quickly trains can come in. A 4-carriage train would take almost as long as an 8-carriage train to pull in, unload, and then depart. So even though shorter trains might be more optimal for suburban stations, there is a bottleneck in the city to stop this from being a practical idea. But this does point us in a new direction, and we can explore solutions for the bottleneck now. Question 5. The PDSA cycle. Why is iteration and learning important? Perhaps it's best to contrast with other approaches, such as waterfall. What are some of the really troublesome assumptions in waterfall? We need to make an unreasonable assumption that we always get things right and can proceed in a linear fashion. Of course, we don't always get things right. An iterative approach is better aligned with this reality, as is recognizing the need for learning. The PDSA is grounded in the idea that our first solution might be deficient. But how could we know until we try it? So we try it on a small scale, plan and do. Then we study the results of our small trial, what worked, what didn't work, and finally act on what we learned. We probably recognize that there are further things to learn, and the cycle repeats. Or we are happy with the results of the trial, and can be confident in scaling it up and rolling it out. The reason the framework works well is because it allows for self-doubt. We don't assume that our first idea is perfect, nor does it need to be. Iteration allows us to learn and to refine the solution. Question 6. Why are predictions useful? The value of making a prediction for the effect of a change before making it is the feedback we get for our knowledge of the system we are improving. So if the impact of the change is similar to what we predict, that tends to confirm to us that our understanding of the system is good. But if the effect of the change is much different than our prediction, better or worse, that indicates that we still have a lot to learn about the system. So the value of prediction is in the feedback we get about our understanding of the system. In questions 7, 8 and 9, we explore the distinction between an improvement initiative and an implementation project, and examine when different elements should come into play. Timeframes and budgets are very solution specific. We need to consider these when implementing something. Defining them too early will cause us trouble. Let's say you are defining a problem and you are told the budget is $10 million. What effect does this have on your thinking? And to the point, what does it do for your consideration of smaller solutions, simple solutions? Very often, a series of smaller solutions will eat away a large chunk of the problem. But if the scale of the solution has been predetermined, we are unlikely to find the smaller solutions, simply because we aren't looking for them. So it is better to postpone the allocation of a budget and a time frame until we have chosen the solution. So what's the counter-argument? Well, investigating the problem itself requires effort and time. How urgent is the problem and what resources do we have to investigate it? From that perspective, yes, some timeframes and budgets might be allocated earlier. However, these would be very different from the budgets and timeframes for implementing the solution. What about question 8, improvement criteria? These answer the second improvement question. How will we know that a change is an improvement? The question is completely solution agnostic, and we should define the criteria in a way that can evaluate many different solutions. The criteria, by defining the improvement we would like to see, also clarify the problem, so it makes sense to include them in the problem definition. As a counter-argument, perhaps we might say that the criteria limit the scope of the problem. Perhaps we are interested in a broader cluster of problems. So if we are defining a problem not for an improvement initiative but for something broader, say the mission statement of an organization, we might not want to limit ourselves by specific criteria. What about question 9? The argument for numerical targets is that they will make us more enthusiastic in pursuit of the problem. However, this has the same problem as specifying the budget. A small improvement target will prevent us from looking at more radical solutions, while a larger target will prevent us from looking at a set of smaller solutions that could collectively achieve it. So what is the counter-argument? When might we want a numerical target in a problem definition? One example would be a specific class of goals which have a numerical element. Usually improvement goals are the increase or decrease of a criterion, but sometimes we want a value to approach a natural equilibrium of some kind. Hence we might have a numerical goal. A simple example would be the acidity of a food product. In our specification we would have some ideal target value for the pH. Getting closer to that number may be the goal of improvement. But if we were to specify the goal as simply an increase or a decrease, we would end up with something that wasn't quite food. And finally, question 10. What are balancing criteria and why are they important? Let's illustrate with an example. A common improvement aim for hospitals is to reduce wait times in the emergency department. Seems reasonable. Until we hear of cases where patients are turned away because the queue was too long. This highlights why we might need a balancing criterion, such as maintaining a level of healthcare outcomes. And what about our train example? Our main improvement criterion is a reduction in the number of passengers standing on the train. The balancing criterion implied in all of our examples is that we maintain the current number of trains in the system. That is, we are excluding the possibility of pumping in great amounts of money, as tempting as that might be for a solution. Okay, so now we return to problem definitions. The first 2 points here we've already discussed. So today we'll be looking at improvement criteria. That is the second improvement question. How will we know that a change is an improvement? And we'll have a whole slide for discussing that. As for multiple perspectives, we've already hinted at this when we looked at systems thinking and the various leverage points that may be available in a system. What is important is to not fixate on one point of view, because that will limit both the understanding of the problem and the range of applicable solutions. So my general advice is to keep working on your problem statement. Rephrase it, reword it, rescope it. Basically, put a lot of work into it. The more work you put into it, the easier that makes everything which follows. This facetious slide came about from my observations across many student assignments. Common patterns of mistakes in problem statements, if you will. This makes for a great slide for discussion in class, but it does make everyone a little hungry, unfortunately. Going through these statements, what's wrong with them? In the first example, it's negatively framed, with the words lack of. You often see this when people are trying to inject a solution into a problem statement. Now, this is a fallacy because the absence of something does not necessarily indicate a problem. For example, when I'm standing in front of the class, I can honestly say, I don't have any food with me. It would be a true statement. You could even test it by searching my bag. So the issue isn't that we can't prove a negative, though in other cases it could be, but rather the fact that I don't have food with me just isn't something to be concerned about. As a correction, we need to use positive terms. In this case, rather than lack of food, hunger would be the appropriate term. Depending on the context, we can agree that hunger is a problem. And you will notice that by making the change, the solution disappears from the sentence. So let's move to the second example. Well, we do see the word hunger here, which would seem to be an improvement. However, what we have is a complex sentence which still injects the solution. And the words can cause or may cause, these are ambiguous, weasel words, if you will. If you have a causal claim in your definition, phrase it as a strong claim, not a weak claim like this. And finally, only because it happens so many times, we have something which isn't even a statement, just a question. Now, in everyday speech, we use rhetorical questions, often to convey ideas rather than truly inquire. But this is completely wrong in a problem statement. One of the important attributes we need in our problem statement is for it to be testable and verifiable. How do you test a question? How do you provide evidence for a question? You really can't in any direct way. So once we have a problem statement, the next thing we need is some improvement criteria. Often a single criterion is sufficient. For each criterion, we start off by identifying the variable. For our train example, that could be the number of passengers standing. And we state the desired goal for that variable. In our case, we want to see fewer passengers standing. For other variables, we might want to see them increase. In some special cases, we would like to see them closer to some natural equilibrium. The acidity of ocean water would be one example. We want to see it closer to some ideal level, because changing it in one direction won't always be an improvement. That's also the only time where it's appropriate to include a numerical constant in a problem definition. In most other cases, it's actually a mistake to put a number in. A very common mistake is to use a threshold. For example, it might be stated as, we want fewer of our customers to be waiting more than 5 minutes. Wrong. Completely wrong. Where did the 5 come from? It's completely arbitrary. The correct criterion would be a reduction in customer waiting time, or average waiting time if you really want to spell it out. Here I would draw something in class to demonstrate why converting continuous data to nominal data can lead to rank inversion. You can see a detailed explanation in one of my articles, Thresholds, the Wishful Thinking Approach to Designing Metrics. There I explore several reasons why using thresholds in metrics is simply garbage. The next point is the measurement method. We need to know how the variable will be measured. The reason is, we want to be sure that we get consistent results, regardless of who performs the evaluation. If our criterion's variable was traffic in Sydney, and we didn't specify the measurement, how would someone go and collect the data? One team might go somewhere in the suburbs, another team will measure somewhere in the city. You'll get very different numbers. Now what you'll typically find in traffic data is a specification of where the data was collected, such as several of the key roads coming into the city. With that specified, any team can go and collect the data and come back with similar numbers. And finally we get to assumptions and constraints. Most data will be affected by several confounding variables. For Sydney traffic, the day of the week would be an influence. You don't want to be making proclamations of an improvement based on a comparison of Sunday and Monday data. In the longer term, changes in Sydney's population would influence the traffic. But in the shorter term, you might note the assumption that the population remains constant. That doesn't mean it's true, but rather points out that you didn't take it into consideration in your calculations. And finally, balancing criteria. These are other variables of relevance, but outside of the scope of how we approach the problem. For our train example, that could be the actual number of trains. The balancing criterion implied in our examples is that we keep the number of trains constant. This is because we recognise the temptation of simply putting more trains into the network, which would of course provide more seats, but would be absurdly expensive. So we exclude that possibility from the scope immediately. Another example could be total travel time. Our current focus isn't on improving that, but whatever solution we introduce shouldn't increase travel time. It should remain constant or improve. Hence, it's a balancing criterion. So here we'd take some time for students to define their own criteria. And one thing I reiterate here is that in most cases you only need a single criterion. Only add more after some careful consideration of whether they're necessary. So how long does it take to understand a problem? It can take quite a lot of time, but it's time well spent because you increase the likelihood that you are directing resources at the right problem. This slide is also a reminder for students of how much time they should direct to their studies. As always, we can refine the problem by asking multiple questions. Many of these refer to scope. Root causes we'll discuss in just a minute. And for exploring the impacts, I would refer you to the Week 2 lecture on systems. One thing that is certain is that you will need to gather some information about the problem. In practice, the data you really need might not exist, and you would need to capture it yourself. Say your customers are switching to a competitor. Well, you'll have the sales figures, so you probably have enough data to confirm that the problem exists. But what is the reason? Why are they switching? Sadly, it's extremely tempting to make assumptions. Oh, the competitor's model has this new feature. We don't have it. That's the problem. Have a meeting for 1 hour and you can come up with 100 plausible explanations. But plausible does not mean true. If you want to know what the customers are thinking, who should you ask? Foodora. So they've had some issues lately, but they grew very quickly in Sydney. Why? The question to ask is, what problem did they solve for the restaurants? After a few volunteers from the class, we usually get to the answer. It's expensive for restaurants to have their own staff for delivery. The staff need to be there and available, but there is a lot of variation in demand. So for a small restaurant, this is rather inefficient. But with a service like Foodora, you're pooling the variation of all the delivery requests from across multiple restaurants. Now, when you pool the requests together like this, the average rate of requests is simply a sum from all the restaurants. But when the standard deviation is pooled together, it's actually less than the arithmetic sum. Or put simply, for a service like Foodora, the rate of demand is more predictable. One of the tools that has remained popular after many, many years is the Ishikawa diagram, named after its creator, Kaoru Ishikawa. It's also known as the fishbone diagram. Now, why is it still a useful tool? Ishikawa recognized that we have a tendency to intuitively pick what we think is the cause of a problem and focus all our attention on that. But we can often be wrong doing that. Perhaps people don't like the manager, so obviously whatever they're doing must be the cause of the problem. Or from the manager's point of view, the staff must be doing something wrong. The cause is with them. And if you're a process specialist, well, everything's a process problem, obviously. For an economist or marketer, the problem's in the environment around the company somewhere. And so on and so forth. We can be very hasty in pointing the finger without taking the time to consider other options. And that's what this tool does. It helps to facilitate the consideration of many different options, some of which we might identify very quickly. But what about, say, equipment and tools? How might that be contributing to the problem? We might need to think about it. And by forcing ourselves to think about it, we can discover a root cause that we would otherwise overlook. Now, a worked example for our train problem. A lot of elements come together to cause the problem. Some of these might be outside of our control, say business hours, roughly 9 to 5 or thereabouts. And in turn, that originates from the day-night cycle. Now, can we get half of the city to work at night? Probably not. So like many brainstorming type tools, not everything that we capture will necessarily lead to something practical. But just like many brainstorming tools, the point is to explore a broad range of ideas, which is why by default we would use these 6 branches, to force ourselves to think about very different areas of operations. The tricky one here was the materials and inputs, which relates to consumable materials. This tends to be more relevant for products rather than services, so it's not a surprise that we couldn't think of something for the trains. Now we should revisit analysis and synthesis once again. A tool like the Ishikawa diagram helps us to work on the problem by subdividing it, that is, through analysis. It can really help to balance this with some synthesis thinking, using the kinds of methods we covered in week 2. By exploring the broader context of the problem, we might discover more productive avenues. This idea was really championed by Russell Ackoff, and we have a link here to a transcript of a really interesting interview. Our research methods we will cover in more detail next week, but one thing that needs to be pointed out is the possibility of doing some primary data collection by the students. This is an option if you would like to collect some data of your own. But if you do, you need to formally let us know. And of course, it's not a substitute for finding existing data. There are many approaches to research. One of the easiest ways of categorizing methods is between qualitative and quantitative, which respectively deal with the interpretation of words and numbers. They are also somewhat aligned with inductive and deductive reasoning, but we'll get into that next week. So what should you look out for when you find data? One thing to be really careful about is anonymous sources. If someone is doing serious research that they are proud of doing, you can be sure they want to put their name on it. So a source without a name is a red flag. Perhaps a few exceptions, but be careful. Next we look at the method. How did they collect it? Is it a method that we should consider to be reliable? Is the sample appropriate? And if there is analysis included, how was that done? Is that appropriate? Then we might ask, why did they collect it? This is really a question about neutrality. Was the study conducted in a way which generates the data that the researcher wanted to find? It's worth noting that the question of neutrality remains relevant regardless of the research method. And there are many other questions to ask if we are using someone else's data for our own purposes. Very often the ideal data set that we need doesn't exist, but we might have to make do with what's available. Now, the extra reading on the slide, this might not be the right slide for it, to be honest, but it's a very good article. Kerr examines how quantitative performance management systems can become really dysfunctional, so I would recommend that as a read. Now, let's look at our train example again. So with Sojourn, we quickly looked up some data about train congestion, and we found this table. Let's go through some of those questions again. So we don't know who the author is, and all we know is that it's published by an advocacy group. So that raises a few concerns. So then we look at the methodology, and all we know is that it's based on the digital tickets, which might be incomplete if there are paper tickets, but that might not be such a big issue. And we don't really know much about the motivation of why it was collected. It just seems to be a bit of a data dump. We're not sure why it was collected. It's a few years old, and we have some concerns because we don't really know who's publishing this or for what reason exactly. But more importantly, it's really not suitable for our purposes. So obviously this doesn't tell us anything about Sydney. Plus our problem is focused on rush hours, so we need more granular data. Your approach to data analysis will depend on the problem and on the type of data you have. But the one thing we do point out is not to use infographics. So in the past we've had some issues with students pasting infographics into their assignments and essentially stating, hey, here's what I found. Now you will quickly notice how these fail our data questions. There is no information about who collected the various pieces of data, no information about methodology. We're missing a lot of key information. And on top of that, infographics like this can often come from activist organisations who are very selective about the data they would include based on the message they want to send. So in short, no. Any number you include in your assignment, you need to be able to explain it. Now, depending on time, we would have students look at some data for their own assignments. The key point that needs to be made here is that you're looking for data relating to the criterion you've defined for the problem. Processes and procedures. We've already talked about these, but just a quick recap. We make the distinction between these as one is descriptive and one is prescriptive. This is usually where I bring up one interesting historical example. So the book of the day is Taiichi Ohno's Workplace Management. Taiichi Ohno was one of the architects of the Toyota production system in the early days of Toyota. Later on it got exported to the West as lean manufacturing, and there's plenty of ongoing discussions about what's right and wrong with the methodology. But I find it useful to go back to the original sources. And Taiichi Ohno had some interesting ideas about procedures. Now, one of the elements of lean is standard work, which is just a different way of saying procedure. But it's really informative to look at Taiichi Ohno's thoughts on this. Yes, standard work is prescriptive and defines how work is to be done, but he placed great emphasis on how it was to be drafted. It was the individual teams on the factory floor that were tasked with drafting the procedure. That required the teams to discuss and to decide on how to standardize the work. But in the end, it was them who owned the procedure, and therefore could take responsibility for further improvement of the procedure. See, if someone else tells you how to do your job, sure, you can follow the instructions, but you won't be inclined to look for ways to improve. But if you and the people around you wrote the procedure, then it's your procedure, and you can change it and improve it. And there we have it, a crucial piece of psychology that we can dig up in an old book. Next we move on to process modeling. The first example we have is just a standard flowchart. Typically students have some exposure to this already, but for those who don't, one of the readings for next week covers flowcharts in more detail. The other modeling approach we discuss is event-driven process chain. This modeling approach is based on interweaving activities and events. The idea is that for each activity there is one or more events which trigger it, and one or more output conditions which trigger other events. We also have additional options for flow control. So in some cases this allows for neater representation of what's happening. That being said, within an organization, the value of any model depends on how many people can just pick it up and read it. A flowchart can be picked up by anyone, with minimal or no training, but how many people in the organization will immediately understand the exclusive OR flow control here? For anyone who doesn't understand it, it's not a very useful model, is it? And the situation only gets worse if we pile on more complex syntax. So keep it simple. Then we come back to the train example. Here we are using the flowchart to highlight where the problem occurs. Specifically, passengers board the train only to discover that there are no seats available. And next we have students draw a process model which shows their chosen problem. Finally, we preview one other tool we use later in the class. The SciPoc is a combination of a process model with a value chain model. So take a simple process like making coffee at a cafe. You take the order, grind the beans, which come from some supplier, make an espresso shot, optionally add some milk, which comes from a different supplier, and finally deliver the coffee to the customer. So this is a useful tool for connecting the process to the relevant suppliers as well as customers. Just keep in mind that the supplier and the customer could be a different team within the organization, depending on what level of detail you're going for. For next week we look at 2 book chapters, one on processes and supply chain, and one on research methods. And as usual, a set of questions to go with the readings. Which brings us to the end of week 3.